building the ability to live away from spaceship Earth. This upcoming test is a big deal. Lots of passion, dedication, and work has gone into the Artemis program on the way to the Artemis I mission. The core stage test is another critical step made possible by industry, NASA, and many AIAA members. Let's delve into this important milestone with Dr. John Blevins, the SLS Chief Engineer. Please use the Q&A function for your questions, and we will get to as many questions as possible following John's presentation. John, over to you.
All right, thank you, Dan. It's great to be here. And first, I'd like to thank everybody for taking time out of their busy schedule to be here to talk about this topic that I love so dearly. So let's get started. Let's go to the next slide. I'm going to talk a lot about Green Run. I'm going to talk some other things about Space Launch System as well. So first of all, just where we come from and what we're trying to achieve here. This is the national asset vehicle that we're building. It's the only vehicle that will push Orion into deep space for exploration. And it's going to be the longstanding national capability. Additionally, I want you to think of SLS as a platform. It will do that Orion mission into deep space, but there's other missions, as I'm going to show you on the next chart as well, that it's set up to do and do well. So let's go to that next chart. All right, so this is our standard view here for how we're evolving the vehicle and the different vehicles in the manifest. I'm going to talk a little bit about this today as we talk about testing, because in the process of building the first one, which is that Artemis I mission, the one you see on the left, the Block 1 crew mission, we're going to be able to certify these other vehicles for the most part as we go along for different elements. And so it's a evolvable vehicle, and the goal is ultimately right at 50 metric tons. You can see on here, we got just a little less than that on this chart that we're outreaching for the Block 2 vehicle to TLI. That's the translunar injection, but it'll be right at 50 metric tons. So it's going to be an exciting capability. And so let's go ahead and go to the next chart. So one of the things on that last chart was payloads. That's one of the reasons I want you to think of SLS as a platform. It'll do those manned missions, but it'll also do missions of national interest. It'll do science missions. And so it depends on where you're going, but this is a vehicle that might help you get there a lot faster. So one is volume. This is a tremendously large vehicle. If I were to show a picture of the shuttle back by those last pictures of the vehicle, you'd see that the shuttle is much smaller. And you'd also notice that even the boosters that are on the SLS, they're 25% taller than the other. And so you can imagine the external tank, our core stage alone before we stack the rest of the vehicle on top is significantly bigger. And so that lends us some opportunity for volume. And this would be particularly of interest for deep space exploration, as we can make some of those parts before we go rather than assembling in space, although there'll probably be some of that too. The mass that we'll throw will be much greater, and you can see here comparisons with Block 1 and Block 2. Block 1 is a vehicle that has some modified other parts on it, and it'll throw 27 metric tons. That's kind of a guaranteed number on kind of a low propellant temperature day and so forth. And you can see Block 2 there is 46 metric tons. And really that depends on the ConOps too. You can squeeze a little more performance, or you can do missions that have different safety features that might take some of that performance back, depending on what maneuvers you want to do in near Earth orbit or those kind of things. You can see on the bottom, we've worked on some missions to go to the Jovian system. And the reason you'd be interested in doing that on an SLS is because of the time lag. If you fly a normal commercial, and these would be the larger commercial, what we call heavy commercial vehicles, you're going to take close to 6 years to get there, and SLS is roughly half the time or less to get there in this vehicle because of the energy that it produces to get out there. So let's go to the next chart. So I want to talk just a little bit about the Artemis I mission. I've got a few of these to show you what we're planning on doing. And of course, this is a combined mission with Orion. Just to speak of a few things that I care the most about as the SLS Chief Engineer. You know, we launch from Kennedy, just as we did on the shuttle with the mobile launcher out there. And very quickly, we get up to go through transonic, and then we drop the boosters. You can see that milestone on here. We used to recover all those boosters. Those boosters were recovered during the shuttle program. The flight rate of SLS with the large volumes that we plan to shoot really doesn't merit that at present. And then as we go forward, you know, we get orbit, and then we'll do this translunar injection maneuver. And one notable thing for SLS, after we separate from the Orion capsule, just after translunar injection, after we send it on its way for its mission, we also have these bus stops. You can see the A, B, C, D, and these are science missions that we're doing on the first flight. And so we'll drop those at those designated locations for science for this particular mission. And let's go to the next chart. So let me talk to you a little bit about where we're at in manufacturing. You know, one of the things that we did in this vehicle is we produced the system, if you will, to make the rocket. And so the boosters are very close to heritage, certainly with the segments. It's an additional segment, but there's still a lot of obsolescence and changes there that had to be done. And as I mentioned earlier, we used to recover those boosters. And so we had those cases from the shuttle flights, and now we're going to be changing, and you saw the Block 2 on earlier, we're going to be changing to filament wound cases because we won't be recovering those boosters. And so that'll be a change there as well. But we've changed quite a bit on these boosters, and we've done several certification tests. The most recent, the first week of September in Utah, we did the Flight Support Booster 1, and we've done qualification motors, and that helps us with the parts that have experienced obsolescence or other changes that we've made in the boosters. And so that's going to be really strong asset for us. Now, the core stage that you see here, that's totally new. You know, I had the occasion to talk to some colleagues at the Naval Postgrad School yesterday, and one of them said, how is that different than the external tank? It'd be an easier question to ask, how is it not different from the external tank? It has the same diameter as the external tank, but other than that, there's just so much that's different. We have a different process of welding. We're doing friction stir welding. We have different materials where appropriate. You know, the thrust takeout structure is different, and we have more thrust to take out. And so the MPS, the main propulsion system that's attached to this, and certainly one thing that's on the core stage that is very notable here that causes a great deal of complication in manufacturing is that we attach the 4 engines there. That part, of course, in the shuttle program was on the orbiters. And so that's a very complicated area of the vehicle. So it's more than just a couple of tanks and an inner tank and a thrust takeout. So this is the part that we've been working on a lot. And it's the part that that we're in the process of testing. And I'll talk more about that for on the green run tests and chart. But anyway, that's a significant part. Then we have some adapters to put the interim cryogenic propulsion stage on, which is a ULA manufactured piece through Boeing. And then we put our Orion integrated vehicle with its service module and its launch abort system on top. Now, you see all these green checks? What that means is that it's been built. And so I'm going to talk a little bit about that and show you pieces of hardware as we go forward. But I do want, before I leave this chart, I just want to say that one of the things that we did in getting back to a new vehicle and flying some heritage components, or you might call them legacy because they're flown in a different way, one of the things that we've done is set up the manufacturing so that we can sustain the vehicle. And so that's really key to getting to where we are today. So let's go to the next chart. Okay, so everything but the core stage is setting at the Kennedy Space Center. And you may, if you're familiar with the posts we've had in social media, you've seen some booster stacking and getting ready. You probably saw those coming from Utah on train. And so there's just, you know, it's basically manufactured and ready. You see the size of just even the boosters, which is smaller than the core stage. You can see that person walking around the scaffolding down there getting ready during stacking operations. And so this is a massive system. Takes a lot of effort. And you see the VAB there on the left, and you see it roll the launch vehicle adapter there rolling out of the VAB, or rolling toward the VAB, I should say, in the middle. And so this is just showing you that the hardware is there and it's getting ready, and we're not holding up. We're getting ready with those pieces while we finish off the core stage verification and certification runs that we're doing at the Stennis Space Center. So let's go to the next chart. Okay, so this is a picture of that core stage. So it's built too, and it's built the way that we intend it to fly. And so it's setting at the Stennis Space Center in the B2 stand. And this is a picture of it, I think taken on one of the meteor showers. If it's videoing for you, you might see a few shooting stars going through. And I'm going to talk about the tests that we're doing there. And so let's go to the next slide and I'll talk about those tests.
Hi, I'm Mary. I'm a project and component engineer working on the RS-25 engine at Aerojet Rocketdyne. In the Green Run test, what you'll be seeing is the SLS core stage powered by 4 RS-25 engines. These engines will be powering the rocket during its 8.5-minute climb into space. Since we're at sea level, we will only be seeing 1.6 million pounds of thrust as opposed to 2 million pounds during an SLS flight. These engines have been used on some notable space shuttle flights. For example, the Hubble Space Telescope servicing mission, as well as John Glenn's flight and the final space shuttle flight. Between the shuttle and the SLS program, the SSME and RS-25 engines have collectively experienced 1.1 million seconds of use. That's more than 12.5 days. This really shows us how reliable and high performance our engines are. These stage combustion engines are really great because by using liquid hydrogen and liquid oxygen, we're creating clean, superheated water vapor, the exhaust of which travels at a velocity of 9,000 miles an hour. That's like going from Los Angeles to New York in just 15 minutes. I hope that gives you some insight on the RS-25 engine and some of the amazing things it can do.
Yeah, I'm really glad she was able to do that video. And let me also just tell you some of the other things before we get into the individual tests on that. I almost timed out. I hope you can still hear me. But in addition to what she said on those RS-25s that we, as she pointed out, have flight history, you know, that engine really has more runtime, more test time, more understanding time than any engine that's out there for liquid rocket engines. So I'm really happy to have that engine on my vehicle. It's a great engine, and we understand a lot of the features of that engine. Let me talk about one holdup. You know, if you've been following us and social media, or you've been looking forward to the Green Run like I have, you've noticed that we got to November and we kind of paused for a minute. And I'm just going to mention one of the problems that we solved. It's really a good story and how we solve problems. And you know, this is a very complex vehicle. The facilities are complex, the vehicles are complex, and we had a valve on the core stage that wasn't functioning the way we thought it should, and so we investigated that further. And on that investigation, we determined that valve could be a hazard to us in this Green Run. Ironically, that valve is more important to a Green Run than it would be to flight. But it was very important for us to go change that valve. Looked like it was going to be a long delay, but this is an area where the NASA teams with the partners at Boeing and their sub-supplier partners that make the valve were able to come up with an incredibly creative solution to create kind of a pseudo green room, a clean room right there on the stand, and replace this valve. And it was just an outstanding effort by the team, and really proud of them, and glad to say that we're back in 100% condition after just a few weeks of downtime due to that. And in fact, as I'll tell you, we flowed our first cryogenics into the tanks on Monday of this week. So that was a very good day for us. So let's go to the next slide. All right, here's the slide I was looking for to tell you a little bit more about the test. You can read all these different 8 tests that are on here. I want to point out a few of them. Some of them are dear to me. I was there for some of them, but I don't want you to think of Green Run as just you know, we built it and then it's a stage acceptance test. It's so much more than that. And in the case of Green Run for us, it's really a design certification and verification test. So there's just a whole lot of verification work that we're doing. There's a lot of certification work that we're doing. There's also still some work that we did that was the culmination of innovative processes and getting to where we are. Like for instance, test 1, it says vibration testing. It's really a modal test. So if you're familiar with that, it's a low frequency shaking of the vehicle and getting the dynamic response and exercising those structures through those displacements. And we were able to do that. That test actually only took 1 day. We had 3 bridge-like shakers on the vehicle oscillating at known frequencies, and we were able to really exercise the structure up around 50 to 60 hertz and then get that dynamic response back. So that really is important for us. It helps us to certify our finite element models. If you're familiar with how this was done in historic manned spaceflight, most of the time this was where you build a complete vehicle. If you've been to Huntsville, Alabama, where I'm at the Marshall Space Flight Center, you may have seen a full complete Saturn sitting inside what we call the Davison Center at the museum outside. And that vehicle was actually built to do this type of testing, to check out that modal test response. But in our case, we used the flight vehicle. We still have one more test to go once we attach this vehicle. So once we get down to Kennedy, there's still some more checkout testing to do and validation testing. But that was a major milestone. And one thing I will say is these finite element models, as we've gotten better over the decades in doing that kind of work, really do match up very well with the structure. And so that was a great thing. There's a lot of avionics. So a lot of our avionics checkout and test have occurred there, interfacing with the facility as well as interfacing with flight software, putting updates to that flight software through the system. It's just been really good. And we have these 8 tests, and the one that you're here to listen to today is really test 7 and 8. And 7 and 8 is where we fill it up with cryogenics and then detank it, check everything out, make sure it's good, and then test 8, which is upcoming as well, is going to be early next year now. And test 8 is lighting off all 4 engines, as you heard in the 2 slides before, and doing a full duration firing at Stennis Space Center. So let's go to the next slide here. All right, so this video, I'm going to kind of talk through this a little bit. It's just a video to show you some things about hot fire. It shows you where we're at and what we're doing. So this is another picture here of the V2 stand. You can see something the size of roughly a Delta Core, I think, on the left side of the V2 stand, which it is used for that too. This stand is at the NASA Stennis Space Center down in Mississippi, just right near our manufacturing facility, which is in just outside of New Orleans. So we manufacture the core stage in the Michoud Assembly Facility. If you're a history buff, that's where the Higgins boats were made for World War II, before it became the Saturn factory in the 60s, and now we use that for the external tanker shuttle. You can see really how much propellant we use. This is a really important thing to point out here, is the logistics of this vehicle. This is not a small tank. It's significantly larger than the shuttle external tank. And so just, tanking this thing up and doing these operations is very crucial for us to have confidence in our design and doing that. So you can see here how this sequence goes for the hot fire, and it also the sequence is replicate for the wet dress rehearsal. And so we just did most of this sequence over the last weekend, and then I was down there as we put our first cryos in the tank earlier this week. And so we go through this full sequence. This T- number is really kind of attached to a launch minus number. It's test minus number in our nomenclature here. But when we launch, these are the same sequences that we will be going through for the full launch of the vehicle, with the obvious exception of boosters not being attached and flying away from the facility. And so that'll be the thing to do there. So. Yeah, let me just let this play out. It's a wonderful, wonderful sequence. Anybody who's been for a launch, you know that seeing a launch, whether that was a shuttle or some of the commercial vehicles or whatever, it's just an exciting event, just wonderful event. And this, if you've ever been to Stennis, I know some of my colleagues may be on, and they've been down to Stennis for a single engine firing. That's fantastic. But when we put all 4 of these on that core stage and light it up, it's going to be real unique. This is a complex test. I don't want to minimize the complexity of doing these kind of tests. We have that much cryogenics, and so we are, and it's flight hardware, so we're being very safe with the vehicle. So we've got criteria for success that may be short of a full duration firing that tests out all the systems early. But if nothing happens in the facility that holds us up, we should be able to do a full over 8-minute firing and get down to the engine shutdown sensors. Now that'll be a great day, and that's coming up very shortly. All right, so let's go to the next chart. Hey, so just kudos to my partners here. If you've got a big rocket, it means you've got a big truck. And if you don't have anything to carry in it, you don't need the big truck. So I've got lots of payloads that we're working on. Some of those, as I mentioned, are cargo. A lot of those are crew. And kudos here to my colleagues from Lockheed Martin and Johnson Space Center and all around the country, actually, that have built the Orion spacecraft. You see the assembled spacecraft here with the service module attached down at Kennedy Space Center. And then you see on the right side here the mobile launcher, and there's been significant testing of the mobile launcher, and they've just done a wonderful job down there. We've tested out the water systems. If you haven't heard it, all that's going on, it's just a really dynamic scene with everything all of these programs are doing to get this first exploration mission. And as Dan said, get back to the moon, space we haven't been in roughly 50 years. So it's going to be exciting. All right, let's go to the next chart. And so this is the Artemis II mission. I've included this in here. It's a little different than the Artemis I mission. It's also it's a human mission. We're going to have people on board this mission. You probably saw the announcement, and Dan alluded to the announcement of the Artemis team. That's a team of astronauts that will be out there supporting us in these flights, going into the moon and around. The specific crew hasn't been announced for the Artemis II mission yet, and then those beyond that. But I'll be excited to see that coming in the next few months. They'll announce those crew members, and we'll be working very closely with them. A lot of what I explained before exists on this flight as well. Probably won't do the co-manifested science missions just for the complexity of that first lunar flight. We'll just wait and see what we do there. But right now our intent is just to fly the astronauts on a pretty good ride right around the moon and bring them home and check out all the systems so that we'll be ready for repeated trips to the moon. All right, let's go to the next slide. All right, so one of the things that I want you to know about is that we haven't just been building the first one. You know, you may have seen a lot in the media about the first one coming through, but we really have gone a long way, not only the second one, but you'll see a slide on the third one too. But you know, all the segments for the solid rocket boosters are there. They're in storage, they're ready to go. They're ready to fly essentially as soon as we stack them down at Kennedy. And we won't do that before it's time, but they're ready. And so not only do we have the second flight of booster segments ready, we have almost all of the, we're only, I think we've got 1 or 2 segments left to cast for the boosters for Artemis III mission. So the Artemis II mission has all of those boosters. The RL-10 engines have already been delivered and are ready and purchased. Our launch vehicle stage adapter is in process and manufacturing, and some of the other things that you see on here, the Orion stage adapters and process. A lot of these have really minor things left to go, and we'll have fully manufactured the second flight of the Orion vehicle. So just want you to know that we're out there trying to get that flight rate up and ready to fly pretty soon after the first flight. So let's go to the next one. Yeah, here's a picture of some of what I just talked about, right? The RL-10 engines, and in fact, these pictures aren't new. I've been presenting occasionally. I think I did an AIAA conference, Ascend, with these exact pictures in them several months ago. So these are existing pictures. You can see some pictures from our Michoud assembly facility there with the forward skirts and the Artemis II tanks. Huge tanks, and you can see some of the other pictures there, completed hardware, and so we're getting that ready to fly. Let's go to the next chart. Okay, so again, I mentioned to you to think of SLS as a platform. If you think about the way that aviation has gone, or any of the aerospace groups have gone, we've really gone from having one-off hardware designs to really using software and other integration methods to be our functional integration, right? So software predominantly can help us shift these missions, and we have this hardware, just like it'd be the Joint Strike Fighter or something, and it can do multi-mission. And that's really the philosophy here for SLS, quite frankly, is that we can do missions of national prominence, missions of national interest and security with payloads. And then of course, you know, the landmark missions that we intend to do on returning to the moon. That's really going to be the cornerstone of what we intend to fly, and is the cornerstone of our current manifest right now. But as I pointed out earlier in the pitch, we're very interested and very energetic, the high C3 science missions. I think we can provide some enabling capability there. I've even worked with the group that does interstellar missions, and we offer some things that no other rocket can do by a long shot there. So it's exciting to be at this point in the program, to have so much opportunity and be looking for those payloads that we enable unique missions. So let's go to the next chart. All right, so I mentioned we're pretty well on the way on Artemis III. I don't show the booster segments here. I show some testing, really that BOLE testing that you may see in the middle there. We'll shout out to our group at Marshall, as well as Northrop Grumman, who's building those engines. You know, that's a 2028 ramp on part of SLS, and we're pretty well underway there. So the good news is, you know, the hard time that it takes in getting the process started is greasing the skids for the rocket to come down the road and be much faster build and much better launch rate as we go forward. So let's go to the next chart. Hey, I wanted to talk a little bit about test philosophy and so forth while I'm here. I know this isn't just Green Run, but part of this is a shout out to some of the members. I hope some of you are on. I've worked with so many wonderful NASA members across the country. I started in aerodynamics, and so you might just see a wind tunnel model in the next slide. And I've done a lot of that work with Langley and Ames, as well as Johnson and Marshall. And there's just a great community across the country, not just in aerodynamics, but in all of these areas. And so I wanted to show a little bit about our test philosophy, because so many of you have been involved in that. And so one is, we started this test philosophy really to feed design cycles, if you're familiar with that, where we go through an iterative process to make sure we can handle the environments, the loads, that we can fly the missions that we want to fly, and assess the payload that we'll have capable for those missions. And so there's a set of tests that are driven by that, and those include aerodynamic tests, they include thermal tests. We even did base heating tests under simulated flight conditions at the Kubrick facilities up in Buffalo, New York. And so just a very unique set of tests there. But you do, through that development testing, you really find out a lot. You know, we did an amazing liftoff acoustics test at the Marshall Space Flight Center. I've got a picture, I think, on the next slide of that. And so the whole point, though, in doing this testing is to do it once, if you can. Testing is extremely important. Analysis is too, but tests are sometimes a one-time event that you get to do. And so the tests were set up with the intent of encompassing that family of vehicles that I showed you, the Block 1, the Block 1B, and the Block 2, or at least providing the submodel validation for all of those vehicles, so that I could qualify all of those vehicles to make life easier as we go forward in manufacturing and flying those rockets. So that's true in the development tests. So when we would go to a wind tunnel, we didn't just test that first rocket, we tested all of them. I remember showing up, I think, with 8 different configurations at the Ames Research Center to test aerodynamics with, and it was just great work. Good job by the team there. Now, the structural tests are definitely the one in a vehicle program type test generally. There, you're going to build something, and where possible, you're going to break it. And you can see on the bullet there that we did break things. And in fact, I don't have the video with me today because we're talking about Green Run. And on Green Run, we don't want to break the core stage, but we built individual tanks on that core stage. And if you haven't had the opportunity to go to YouTube, just go to YouTube and search liquid hydrogen test to failure, SLS liquid hydrogen test to failure. And you will see just a fantastic video. And let me just give you a cue on that video. The first thing we did is test the failure, and that's the buckling that you may see. If you get the full length video in there, you'll see the buckling, but that creates a critical flaw size. And that critical flaw size, as you unload that vehicle, kind of a dance between the pressure that's in the tank that you've tested to, which in our case was just 5 PSI, so a reduced pressure, and then the millions of pounds of compression that we put on that hydrogen tank. And when you do that dance of unzipping, you know that you're probably going to have the catastrophic, kind of unzipping, and we did, and it was quite dramatic, and that was what we intended. And so we learned not just about the buckling mode that you see initially in that video, but we also learned about the unzipping with critical flaw size. Very good test, just fantastic. We did a similar type test. The oxygen was a hydrostatic, so we we burst that one with water in the tank, and so that was great. And we also tested the core stage engine section until it broke. And that's a very complex structure, unpressurized, but very unique to see the where the weak points are, where it was going to rip. And those structures came out well above our 1.4 factors of safety design margins to not only the first flight, but the future episodes. So now we know with those future vehicle geometries where our margins are is great. And then there's other kinds of testing too. And some of you on board may be involved in some of that. We do qualification testing. That's where we'll go in and test the most extreme environment that we expect with margin. A lot of these are vibration tests or thermal tests driven by those unique trajectories. And then subsequent to that, what I don't have on here though is acceptance testing. A subset maybe of qualification testing is doing the acceptance testing of the individual parts as we get them. And then the last bullet I have here, and I have it on purpose, is integrated avionics and software to talk about. And I don't think I included a picture of our systems integration lab, which is where we do software, but it's really critical as we get to these systems that have software as the functional integrator of the vehicle, as I mentioned, to really have a replicate to your vehicle in a laboratory environment. And so in our case, we have the same cable lengths and the same orientation, if we can, the same relative position of all of the boxes that are in our instrument units. And so that would include even the rate gyro assemblies and all that. And we will do our full fly-ups and simulated fly-ups in that integrated avionics and software testing. And so that end-to-end type testing where you have overlap can really help prevent failures. And if you're familiar with launch vehicle history, you know that software can be a really important part. In fact, shuttle during the first flight, and they got out the pad in late 1980, and they sat there for a long time working on flight computers and that kind of thing. So we've got that same risk that any vehicle has, and we are working it. And the way we work it is doing the most end-to-end testing that you can do, all the way from the sensor to the effector. And what's in between that sensor and the effector is that software and the measurements. And we're trying to simulate that best we can. So it's a pretty neat laboratory. All right, let's go to the next slide, and I'll show some pictures, I think, of some of the testing. Just to give you an idea of some of the testing, and of course, it's a little heavy in the aerodynamics side because of my specific interest, I guess. But some people don't realize the kind of testing we do, and some people think that we're doing all computational work, but that's not true either. And you can see that on the bottom left here. A good friend of mine, Martin, is in there with the model, and he is, and that's roughly a 13-foot model, and you can see it's a cargo configuration of the Block 1B version there of the vehicle, and that's the transonic dynamics tunnel at the Langley Research Center. And we're testing the low frequency unsteady aerodynamics. So that would be the shock oscillations and resulting response of the vehicle, which can be both loads and GNC. Controls can get an uncommanded steer from those shock oscillations. And so we test that through the full flight envelope down there. And so, as I mentioned, we're not just testing for that first rocket, which you see above that in a shadowgraph form. And that shadowgraph was taken at the Ames Research Center. And that model is not much smaller. It's about 11 foot long there at the Ames Research Center. You see the shadowgraph there. And that was a higher frequency unsteady aerodynamics test that went up to Mach 2.5. So very similar physics there, but caused by different things. Differences maybe, turbulent boundary layers and vortex shedding on the top picture there, and looking for the shock oscillations on the bottom. I mentioned, in staying with the development testing theme, I mentioned that scale model acoustics test performed at the Marshall Space Flight Center. And this test, not only do you test with pad simulated and water simulated, as is shown in that center picture, but you also lift that simulated test up and drift it, right? So your maximum vibration a lot of times in a rocket is certainly just after you lift off. It's not when you light the engines. You may sustain more vibration at other phases of flight, like transonic, but a lot of times you'll drift out over that pad and you'll have a high reflectivity environment for those sound pressures, and that's a critical environment to understand and make sure you qual your parts very well. And so that's just a really exciting and difficult, challenging test that was performed at Marshall Space Flight Center. These other pictures you see here, I mentioned that video. Hopefully that picture on the right with the hydrogen tank ripped open will just make you want to go to YouTube and look up that video. That was very dramatic. And imagine there was only roughly 4 PSI. The test was done at 5 PSI, but we were unloading the pressure. in the tank, knowing that we had a critical flaw there when that final rupture occurred. And you can see the energy with the kind of volume capacity in a tank like that from very low PSI is just tremendous. And on the bottom, there's the liquid oxygen tank. On the bottom, smaller picture, the one we hydrostatic tested to higher pressures and different loads. And so all of these give us a lot of information. They give us stiffness. They give us influence coefficients. They help us validate finite element models. They also let us know where our margin is. They let us know where we can take out mass to improve the rocket as we evolve that to do the missions that I mentioned. For instance, the hydrogen tank has quite a bit of margin in it. I mentioned earlier, that we're looking at 50 metric tons for that block 2. Well, some of that margin is going to be discerned out of some of these tests, and we can go back in and we can reduce that mass. And additionally, once you get very good with your rocket, you can take some of that developmental instrumentation, and you can take some of the measurement systems, the data acquisition units and cabling. There's a lot of mass and cabling on the first flight. And so anyway, let's go to the next slide. I could probably talk about testing for hours. It's one of the favorite things that we do. The bottom line here, this is a picture of our Launch Command Center down at Kennedy Space Center. That's actually Charlie Blackwell Thompson in the bigger picture. She's our launch director for the Artemis missions. Just a wonderful, experienced leader down there with this team that'll be ready to launch the rocket. They've gone through several simulations, and we can't get there without them. I'm excited that they're there. And really, as I do this job, it dawns on me that we're really trying to grow the vehicle for the next 30 years, for the next generation of engineers, for you guys that might be on, to use as a platform to do science missions, to do these missions of national interest, as I mentioned. It's really an exciting time and an extremely capable and reliable vehicle as we develop it. Let's go to the next slide, and I'm going to mention just a few things as we get off the stage here and hopefully answer some of your questions. You don't do this. I've heard people describe the vehicle being developed in Alabama. That's not true. It's developed by the United States of America. And you can see here the distributed group of people just in building the rocket and the sub-suppliers. But for what I do and the people I adjudicate, they're all over the country in terms of our NASA team, in terms of our supplier teams. They're doing outstanding work. And it's just a lot of partners, just like we needed to do in the Apollo program with the Saturn rocket and the Apollo capsule. We just have an amazing number of participants in this that make us all stronger. So we seed a very unique set of technologies that continue to grow as we do this work, and we just have incredible partners. And so I've got a shout out to all you folks in doing this. The work that you're doing, as a chief engineer, getting to represent you is an amazing privilege. Let me also say in closing, this is my last chart, Dan, so you can get ready to jump back in with me. I just want to put a plug in for AIAA. I'm an associate fellow of AIAA, been part of AIAA since I was in graduate school. I worked a few years, I went back to graduate school, and I joined this organization that had a lot of letters, and I learned from that group. And I will say to you that if you're in this industry and you're an engineer and you're trying to do it all on your own, you're missing out, and you're not going to make as much impact. AIAA, organizations like AIAA, but particularly AIAA as the premier organization in our industry, is really the platform which we can stand on, we can work together, we can grow the science, and we can achieve more. So Dan, thank you for doing what you're doing at AIAA.
Oh, thank you, John, for that great presentation. There are lots of comments in the question and answer section that's complimenting and very thankful for your presentation. So we really appreciate it. And we have lots of questions. There's no way we'll get through them all, but we'll get through some of them. I'll start with the technical, and then I'll work out from that. One of the technical questions in here was, does the core stage green run test, John, does it put any unique environments on the system that are actually easier in flight than they would be on the ground test?
Hey, great question. Kudos to whoever asked that one. Yes, it does. That's just an artifact sometimes of testing. But in this case, for instance, our base heating, on the core stage, will get significantly lower later in flight, but we're going to be setting in a high density environment with high reflectivity, just setting on the ground. Also our vibration, we're setting there at, doing structure-borne vibration. And so there are several things that we will put some miles on the vehicle by doing the test, if you will, and that are considerably different. So we went through a design and analysis cycle just for the green run, just to verify that we could take those different loads and accept those loads and vibration and heat. And so, yes, that's a great question. And there are those, and I just mentioned a few of them. There are several more, but of course, the flight itself has more loads and is more strenuous overall. But there are certainly things that you've got to pay attention to on the green run. So yeah, good question.
Good, thank you. Another technical question is, what were some of the technical improvements made on the RS-25 compared to the shuttle SSME configuration?
Hey, that is an even better question than they might think, because we're in the process of going through an evolution in the RS-25. So first of all, the ones that are flown on this vehicle, as you may have heard by the Aerojet Rocketdyne engineer being interviewed, they've flown before and they flew on shuttle. We did make changes to the controller, so they aren't strictly heritage the same way that they are, so we've changed the controller. We've also changed what we would call the rated power level that we fly at for these vehicles, so that, because we're not going to get them back, we have a lot of history with them. We know where we can push the engine to very easily. Under shuttle, as Dan knows very well, we wanted them back and we didn't want to do as much refurb, so we were easier on them. So we are pushing them to a higher rated power level. We've changed the controller, and that's just for the initial flights. After the 16 engines that are based a little bit more on the Space Shuttle main engines are finished, we will have numerous upgrades. These upgrades include more manufacturability, generally lower costs. Printed parts is a big emphasis with us. And we're increasing the manufacturing rate. Something that's not really easily known or intuitive may be that we never built a lot of engines in a single year for shuttle because we kept getting them back. And now we're not planning on getting them back. So we're going to make them cheaper and easier to manufacture so that we can fill that need for SLS.
Great. This will probably be the end of the technical, maybe, and depending upon what else comes in. To the modal test, how did you guys determine the frequency levels and determine to do the modal test using the flight hardware and then with whatever final checks you need to do down at the Cape?
Well, really, that's a great technical question. I love that question because modal it's a complicated thing, right? So if you're familiar with Saturn, we actually brought it up here. We had it on shakers. We did different tank fill levels. There is this one really interesting aspect of SLS that the former chief engineer, good friend of mine, Gary Lyles, used to say was a chief engineer design stroke of brilliance. But one of our primary control nodes goes right through the LOX tank, which is where all the mass is. So one of the things we discerned very early is the tank fill levels didn't significantly change our displacements, our mode shapes for control. And so we're able to get away with flight hardware without different tank fill levels and still have very good confidence in our finite element models. And so really what we're doing is we picked frequencies up to 60 hertz. So we're hitting all the modes that the finite element models would tell us up to around 60 hertz. Now, as you get higher in frequency, the vehicle itself acts as a filter and really absorbs some of those. There's more damping at those higher frequencies. So it's really those low frequencies that we're targeting. We're targeting, the longitudinal mode for, for controls. We're also targeting some of the secondary structure where we may have had concern about response from shelves in certain sections. So it's really technically driven, and it's a combination of loads and flight control that tell us what we need to go validate. And so, another comment to that question, Dan, and I'm hogging the stage here. I know you've got more questions, but when you do tests, it's very important to note that you're answering questions. You're not demonstrating, you're answering questions. And so those modes and the modal are very specific to the questions of that vehicle that were driven out by our controls analysis and our loads analysis. during these design cycles. And I will say that those questions and now the answers are converging, which is really great news for the finite element model. So I hope that answers that person's question. Great test.
Really good. Thank you, John. What, give us a sense, the tests that you guys are running on this core stage, will this be the same set of tests that you'll run on every core stage before flight, or is this a one-off approach for the future?
Green Run as it stands is a one-off test for the future. Now, when the shuttle was developed, they had a thing called the main propulsion test article, which simulated a lot of the main propulsion system, and they had it at Stennis, and they would occasionally go back and answer questions. As I mentioned, every test is about answering a question, and they answered questions with that test article. We may, as we go forward, have more questions, and those questions will derive into specific tests. But the Green Run as a whole is a design certification test that encompasses all of those vehicle models that I showed you, and it's a one-off test. We won't be doing that again. And so that'll make us faster to launch too. We'll get the hardware to the Cape a little faster on the next one.
Okay. You mentioned early on that the boosters themselves were not going to be recovered by SLS. Can you describe the reasoning behind that decision compared to the fact that those boosters were recovered in the shuttle program?
Yeah, it's really a combination of launch rate. It's more of a financial decision, actually. If you're going to have a fleet to go out and get the boosters and bring them back, that's going to cost some money. It's also a launch availability question. You know, if you are familiar with shuttle or other boosters that get recovered, sea state becomes a requirement. You know, you may not want to recover the boosters at 12-foot seas at their location coming down. Generally about 6 feet seas is about the most that you want to recover. So there's a lot of technical reasons like those launch availability. It burns into launch availability. But the main reason is that you got to maintain the crew, the expertise to go out and get those and bring them back. And in our case, that break-even point is several launches a year and not one. And right now our manifest is a launch to 2 launches per year. And at that rate, it's just smarter to let the boosters go.
And you've talked about how the manufacturing is set up for sustainability in the long run. Can you tell us some of the things that were put into the design from the front to make this a more sustainable design? And also, what do you think is the production rate per year for core stage and SLS?
Yeah, I'm going to answer that in reverse order. I'd like to see 2 a year. I'm just going to tell you right now, I'd like to see 2 core stages, 2 SLSs a year. You know, if you've got a rocket this big, you've got to have a payload to fly. And so you're not going to fly 13 SLSs a year like Shuttle did achieve 13 flights in one particular year. That's not our goal. You know, we're not just going to keep sending SLSs up. You've got to have good payloads. So 2 a year, I think, is a great mission profile. I think that serves our partners well. Some of the things we've done to achieve that, for instance, I'll start with the engines. I'll start with the West Coast out there at Aerojet Rocketdyne. Great partners is the printed parts that they're working on and the manufacturability of things like a nozzle that could be channel wall instead of tube based. And so there's a lot there that could make that more affordable and quicker to produce. For the core stage itself, one of the things that we did is we designed it to handle the loads of those future vehicles. So in the early flights, in the Block 1 flights, that embeds mass into that stage that is unnecessary because you don't achieve the loads. You don't have the heavy payload. So your very simple load, the F equals MA load, is not the same. But we built it to handle the loads to do that future flight. And so we don't have to change that as we go forward. And so those are some of the things that we've done to make it achievable. But I want 2 flights a year, Dan. So you help me do that, all right?
Believe me, I tried. In my past history, could you describe for us maybe how you go through the design process, or is it different between a launch system that's set up for cargo versus one that's quote human rated for an Orion crew flight?
Yeah, absolutely. You know, there's a lot of overlap. So we're going to have a unique cargo vehicle in reliability, right? Because the difference that you have for a human mission is the reliability and the factors of safety. And anybody can download the human rating requirements that exist on the NASA website. You can all go take a look at that. And there's also other documents that are out there that will support you if you guys are interested in looking at human flight. And one notable one is NASA SP, I think it's NASA Special Publication 287. It's what made Apollo a success. And so some of those requirements, which are in the human rating requirement, and some of those other tidbits, which are in that special publication, talk about simplicity. So that's one of the reasons that SLS is set up to do one launch and carry multiple payloads and multiple missions, just like Apollo did. That was, at the end of the day, that's why they didn't go for the Nova rocket and why they didn't go for Earth Orbit Rendezvous, was the complexity and having multiple missions. Apollo felt very strongly that having one mission helped them. And that's what's embedded in part of that mission, the human rating mission requirements as well. But we will have some of our structures that will be good to loads that exist beyond what you require for cargo. But we will be different on the specific parts that are cargo, that aren't overlapped. So payload adapters, the cargo mission itself, we won't have to test to the same margin, and that will provide some relief for the cargo compared to what we consider the human rated mission to do, Dan. So just to give an example, we tend to go with a 1.25 to 1.4, somewhere between the two, structural factor of safety for cargo. We always exceed 1.4 in our human rating for the flight that we're doing for our human rated flights.
Good, good. Are there any plans to make parts of SLS reusable down the road?
Well, it's certainly capable. We've done that before. If you go back to the legacy program that we're building off of on some of the parts, like shuttle, as you know, Dan, we recovered everything, right? So it was the orbital recovery vehicle, and there hasn't been another one like that because it had the engines and everything. So it was a fully recovered vehicle, and I know other people are working on that, and I think that's great. So it's certainly capable based on that heritage. We understand as an agency and as a workforce base, one of the things I want to point out is NASA doesn't build the rocket. We have all these industry partners, the commercial partners that build the rocket, and they're very capable, and they've done that. And so if it merits it, I would love to do that. I think the goal for SLS should be to get flying and to get the right number of payloads. If those payloads merit reuse, certainly the boosters are an easy one. I've already got all the capability to put the parachutes in, or however we choose to do that back in. And then certainly, you could recover, say, engines and a partial stage instead of recovering the tanks and those kind of things. So that has been talked about. It is on our radar. And if our stakeholders at headquarters and Congress and all want us to go do that, that's an achievable mission. It certainly costs money to do that. It is not a free effort. And so it's a trade. And with the flight manifest we have today of 1 to 2 launches per year, it doesn't quite meet that metric yet, but I'm certainly willing and able to go execute that mission. Good.
I'll ask the question everybody would like to know an answer to is, when's first launch?
Well, we're going systematically through this checkout. I believe we are publicly, you may know publicly what we're saying better than I do. And so I believe that public data is July. And there are challenges certainly that stand in the way of that because of the systematic way that we want to certify the vehicle. Not that we could not do that. I believe we could do that. And so it'll be sometime in 2021. We will be launching this rocket around the moon. It's going to be an exciting day, and I invite you down there to join me, Dan.
Trust me, if I'm invited, Dan will be there.
Okay, I'll get you a Causeway Pass or something.
Oh, can I get into the control room? That's where I'd rather.
Well, I did realize I said with me, and I'll probably be in the launch control center. So maybe not exactly with me. You've been there before, though. So
one last question that I always like to ask is, what advice, given your career, and certainly greatly appreciate the shout out for AIAA, what advice would you have for students and young professionals to get involved with space programs or space projects such as SLS, Orion, and Artemis? What kind of advice would you like to give the up and comers?
Oh man, what a great time to be a rocket engineer, as I say, or a rocket scientist. We've got so many different platforms that are going now. You've got SLS, you've got the Commercial Crew programs. You got launch services. We're looking at going back to the moon. You know, if I were a young engineer today, I would consider graduate school. I think it, and I did go to graduate school, as you know, Dan, and so I think it helps tailor you into those interests and provides more opportunities. I would consider that. There's so many wonderful universities that specialize in this. I would join AIAA. I would very strongly get part of the AIAA community. I served in the technical committees earlier in my career. You can volunteer and be a non-voting member with many of those technical committees. I think that's a wonderful thing to do. If you have the desire to work in this industry, there may be many people that tell you it's not good, or maybe you can't get a job, but you're always going to find naysayers. Have some resilience, seek out those opportunities, fight for them, and when you get knocked down, get back up and keep working at what your goals are. And that's what I would tell you to do.
A great segue into follow your passion.
Follow your passion.
That's the way it works. Well, John, I just want to say thank you very much. And for everybody online, just for your awareness, the recording of this will be up on the AIAA website here in the not too distant future. We'll get it up as quickly as possible, so that there have been lots of requests for slides and other things. The best thing to do is to go to the link on AIAA.org in order to get the website. John, I just can't say thank you enough for taking the time to do this. It is personally gratifying and very exciting to see this test coming to fruition, and also to see the great progress on Orion and ground systems and all of the getting ready for that Artemis I mission. There's been a lot of hard work you guys have put in, the industry team, all of the engineers, and the whole team, not just the engineers, but the procurement people, the finance people, the test folks, and I'll get yelled at for skipping somebody, but the whole team is done, and you representing the team. We just want to say thank you for what you're doing, and stick with it, and we look forward to the success.
All right, thank you, Dan.
A couple of closing notes is, again, thank you to everyone for joining us. Please tell your friends, colleagues, and even your family, if you'd like, about what you heard today. It'll all be recorded on the website, or the recording will be posted on the website, like I mentioned. I want to remind folks that upcoming in January 11th through the 21st will be our SciTech Forum, where we will have over 2,200 technical presentations and continue these important discussions on all aspects of aerospace technology. And also a great set of plenary speakers, one of whom is actually going to be Eileen Drake, the CEO of Aerojet Rocketdyne, the people responsible for those engines that we're talking about. And we look forward also to the upcoming Ascend events. Ascend 2020 was a great success, even though it was online, and we're preparing for Ascend 2021. And we'll continue to see the progress there. And hopefully we're either talking about a flight that happened or talking about a flight that just is about to happen. Look forward to that. And also make everyone aware that come January 26th, on the recruitment front, AIAA will be hosting a virtual job fair. So please take advantage of that if you're interested. And you can also continue to study space topics more in depth with online courses that, again, are on the AIAA website at aiaaa.org/events-learning. And you can continue to grow and follow your passion like John's talked about. One more time, thank you, John. Thank you to the NASA industry team for everything that you are doing. We look forward to that great success. AIAA is here to help make everyone successful. So just want to say thank you one last time, and everybody have a great rest of your day.